information of simulation. If am I audible?
Yes, sir.
Okay, fine. So what I'm saying that I assume that you all people are aware with MD simulation. So today we will see some little of couple of slides that will be explained why we need to do the MD simulation. Then why we need to do the MD simulation of protein ligand, and then we will go for the step, and then we'll go for the analysis. So as we know, that all the biomolecules, whether protein, carbohydrate, all these things they are in dynamic in nature to just perform their biological function. So in experimentally, if to understand the structure, there have the usually two methods are used, that is the X-ray and NMR, and another is the electron microscopy. But for X-ray, we are getting some static events. So if we have a little bit information about the structure, how we resolve the structure of biomolecules in X-ray, technically we can say that the entropy tends to zero, means the molecule is going to be frozen in a particular state, and from that state we are taking a snapshot, and then we are drawing the 3D coordinates. So whatever results we are getting, whatever the structure we are getting from the X-ray, that is the static. NMR, by applying an NMR, we will get the dynamic state, means the movement in the protein be able to capture. So that we call it dynamics, means be able to capture the movement of protein or biomolecule. Then we are going to be said it is in dynamic in state. Similarly, electron microscope, you will get the any particular one state of the protein. But proteins are movable to perform their biological function. Eventually, when they interact with the ligand, they also do the some modulation. So for that, what would be the some alternative? So MD simulation can be used as an alternative to understand what the molecular interaction going in between the protein or protein ligand or whatever the biomolecule as a system you are going to be select. And simulation little meaning that simply I am going to mimic it. So what exactly happening in the biological system that we are going to be mimic by applying the simulation. The term MD, that is the molecular dynamics, means whatever the biological system in our body, they also follow some thermodynamic states. So that is regulated by our thermodynamic state. So that from that information we are going to take from there what happening in the biological system. That is exactly what if you have remember this thermodynamics we have learned in the in chemistry also and the physics also, but little bit more chemistry point of view. Here we have to think how these two molecules going to be interact. So exactly what happening in the chemistry lab, like the carbon and oxygen will combine, then the CO2 will form. So what the motion will be there. Similarly, if there is molecular interaction, so we know that whether protein or your carbohydrate, that is the made of the some atoms like carbon, hydrogen, nitrogen, oxygen. These are all the constituents of the amino acids. So then they will interact with ligand, means ligand has also constituted with the different atoms like carbon, hydrogen, nitrogen, sulfur, depends upon the nature of the ligand. So when they will interact, so it is exactly happening as the atomic interaction. So that atomic interaction is very fast, and that whatever the left right side corner, you can see that some thermodynamic. This formula, forget about the formula, but we have to read that if some experiment is going on, some chemical reaction is going on that need the optimal temperature, optimal pressure, and some energy is required to accomplish the chemical reaction. So similarly, similar things is happening in our biological system. Similar things is happening in our own body. Then another thing is that the force field. Force field is the very important constituent of the any MD simulation. What force field will apply is some force field are common generally. If there is no any specific required, then we can like charm 37, charm 36, like that, charm 27. This or bromose, these are the some common force field. But if we need to some accurate result, then we have to apply the accurate force field. Because if you are going to simulations later on, I will also explain when I will come there. In simulation, we are putting a molecule. It's the best you can understand from here in the first slide. So this you can assume as a simulation box. Or in the simulation box, you can here we can see that they have the protein in the center of the box, and around that, whatever the red dots you able to see, that is the water molecule, and some blue and green dots are there. So that are some ions we have put it here. So I will explain to why we have added the ions and all these things. So now come to the point that when we have to simulation, then we are just putting any molecule in a system, and then we are applying a force field. You have remembered that when you will apply a force field, so if they have any charge in the system, it will be affect the force field. It's a clear to all of you. Actually, this is the two-way communication. So if you have anyone has any problem at any state, they can stop and they can ask me. Okay. And I will be also communicating between that. Okay, fine. So if they have charge in this, if they have charge surrounding and we are applying a force field, it will be maybe deflect. So for to neutralize the system, we add the counter ion. Counter ion. So then again question is to what counter ion we can add. We usually add the sodium and sodium chloride. So when we are doing the experimentally, we usually use the buffer of the NaCl, and that is the 0.15 molar concentration of the NaCl solution is used as a buffer. So same things we are going to be add while the simulation. If anyone interested in the formula, then like whatever the equation is written here, then I can go in detail. But this is the general overview that when we are just doing the simulation, so there have the some action of the particular force field that is more important and required to be selected there. Okay, it's fine. And you know that if they have the, because why this force field? Because they have this motion. Motion means when we are calculating, so we also calculate the displacement. And when displacement, and then when the molecule will move, they have the velocity, and the second derivation, they will get the acceleration. So from that things is used. But what difference is here that we are just integrating, because when we are writing a formula, like we are just take the Coulomb law. So when we are talking during the Coulomb law, what we are taking only two charge. But if you will take the structure of the protein or DNA, then you will get the many charges is there. So what we have to do, integrate all these things. So when we do the calculation, during the calculation, we integrate all these things. But here, this formula is given for the considering as the simple one atom or two atom. But one atom, two atom, but we have the many atoms. So we are just calculating for each atom, and then we are integrating it. Similarly, if molecule is there, they have the potential energy. When you will apply the force field, the kinetic energy, that the potential energy will be converted into the kinetic energy. And then we are calculating while doing the simulation, what is the change in the velocity, what is the change in the displacement, and that will be help us to just understand what is the interaction between these two molecules or two atoms. Now see, while force field, what the parameters we are considering when we are applying to the force field. So we know that if they have the carbon-carbon bond, so they have some particle distance. So we have to apply force field such as that this actual bond between the two atoms is not going to be distorted. So what going to be changed? Their bonding angle is going to be changed. Their torsion is going to be changed. Isn't so? So like carbon-carbon. So if some atom is going to be attached with the carbon, so its weight and the volume is going to be influence the carbon-carbon interaction. So for the when we apply the force field, it will be going to be rotate, and actually it's happening in the nature. Okay. So these are the and also these are not only the force like bond potential and the bond angle potential, torsion potential, and Lennard Johnson and the Coulomb force. Evenly, we know that there have the two major interaction when we are looking for the protein and ligand. two major interaction we are taking in the consideration. One is that the hydrogen bond interaction and another is the hydrophobic interaction. These are the two major interaction between the protein and ligand, and these are, we can say that it not stable like that. It is not permanently going to fix. Like if they have the covalent bond, that is the permanent bond. So that interaction, you cannot say that when you will simply apply, and if they are involving interaction, their covalent bond is going to be distorted. If the covalent bond is going to be distorted, then the entire structure of the molecule is going to be distorted. So we are not going to apply any force field like that. It only going to be disturb their covalent bond. But what is our interest? Our interest is that interaction. What interaction is favorable to perform the biological function. And for that, we focus usually on the torsion, and the linear torsion also use a hydrophobic interaction, that because ligand has to be go and sit at the active site of the protein. So protein ligand interaction will decide which ligand is more favorable, more potential against any particular target. That we actually, I hope you all be aware with the docking analysis. So before to perform the MD simulation, we usually perform the molecular docking analysis. And in the docking analysis, what we are doing, we are selecting a active site, and against the active site, we just put the molecule there. And then we apply, again, we are also apply the force field there also. But condition is that usually while doing the molecular docking, we put the protein as a static condition and we apply the force on the ligand to just generate the different conformation. And the same grid I have defined here ki box. So similarly, we are creating a box over the protein active site that is defining the area where the ligand will go move freely, and we will calculate the different potential there. Depends on the atomic interaction. Based on that, we are getting a score, and on that score, that is called as the docked score. And based on the docked score, we are selecting that which compound is more favorably or especially well fitted at the active site of the protein. But again, question is arises, why after doing the MD protein ligand docking, molecular docking, you need to do the MD simulation. The question is why? Because the question is this arises because protein is a static in condition, and in the slide I told you that the protein is in the dynamic in nature, and actually it is in nature, it is in dynamic state. So whatever the calculation we are getting here, and we can claim that any particular ligand has this much specificity. Like I'm taking just taking the 20 kilocalorie per mole as a higher, that is showing here the best. For example, I am taking, and the lower cutoff I have taken the 10 kilocalorie. While if we are doing the virtual scaling or selecting the thousands of ligands is given there, and out of that we have to find who is the best ligand against any particular target. So we have decided at their cutoff key if any ligand. So we will first do the docking and we'll go the higher, what the higher value of the delta G, that is the docking binding energy is coming. Suppose it is getting the 20. So up to that we have go up to the minus 10 kilocalorie per mole. So that cutoff we have taken. Whatever the ligands is lying in between that, we are assuming that they are good in nature. Okay. And on that basis, just we have composed or we have just planned to go on the experiment. When we are performing the experiment, we find that out of these ligands, they are not showing the activity in the experiment. Yani ki wet lab experiment, these compounds are not going to show you the good activity, good results. So what is the reason behind it? The reason behind it that when we have done the molecular docking, the protein was static and we have moved the only ligand. Most of the tool evenly, some tool evenly glide. They are just allowing you to put the flexible of some particular residue. It is not the entire protein is going to be flexible while doing the molecular docking. So this is the one of the drawback of the docking, but yeah, docking is very good tool and important tool in bioinformatics to see the molecular interaction. Evenly after the simulation, if you will get some result and you have to check the interaction. So we can go again and we can check that, okay, this conformation has this interaction. The benefit is of MD simulation is that we will get the different conformation with respect to the time. Okay, so then we are getting the different frames, different conformation with respect to time. So we concatenate that and we can see that which interaction is more persistent during the simulation. And if any interaction is more persistent during the simulation, we assume that we pretend that that interaction would be the more stable interaction while the protein ligand interacts. Okay. And for that, this charm GUI was one of the another tool. So charm GUI is giving lots of references there. You can go there, you can visit there, and you will get all the details of the phosphate parameters there also. And as well as when we perform the MD simulation, so we usually took the two tools we usually use for the MD simulation. One is the Bromax and another is the Ember. Today we will see with on the Bromax. And so we will do today hands-on with Gromax, but another tool is that your Ember and NAMD also some another tool. So different tools. So when we are doing the simulation, more important thing is that the parameter just defining the parameter of the molecule. So you will see in the step. So just here only just remember that there have the charm GUI where you can go and you can generate the parameter file. So for that I have just put it this here the charm. So I mentioned that when we are going to do the simulation, so the interaction of the molecule we are taking first as a water molecule. Why water molecule? Because our human system is aqueous in nature. Okay, so we have to consider the water molecule, and especially if we are going to be related in the terms of molecular interaction. So again, one lacuna in the docking that when we are doing the molecular docking, we are not giving any ambient condition like implicit or explicit water environment. So there have the in vacuum condition, like there have the only protein and ligand. But you know that the interference of the water molecule also influence the molecular interaction, like the polar interaction means hydrogen bond interaction, or evenly in the hydrophobic interaction. In both conditions, water play a very key role, crucial role for the protein ligand interaction or the protein or two biomolecular interaction. Because, for example, if there is the hydrophobic, so what you assume that if there have the water around that, so what will be effect on the hydrophobicity? Anyone? Any applicant? Suppose that we have a system, we have the protein and ligand, this interaction is there. Now we have added the water there. So what effect you are assuming that? What things going to be changed there? If we are talking in the terms of hydrophobicity. Any applicant? No one. Anyway, see, when like there have some amino acid residue there, it is exposed, is exposed like this. So once it will be come into contact of the water molecule, what they will go deep down. So their conformation is going to be changed. Okay. But if there have the two system in between that water molecule is there, so it is going to be enhance the polar interaction. Polar interaction means water bond interaction. That is going to be hydrogen bond. You can say the hydrogen bond interaction that is going to be enhanced. If I hope carbonic anhydrase is one of the enzyme in your body, everyone body also that regulates your pH of the blood and that used to carry the CO2. So we know that how it's going to be regulate the pH. There also these things is going to be applied there to maintain the pH of the body. Then another important thing is that how before to start the MD simulation, how we will select a simulation box. And simulation box is depends upon your size of the protein. Some proteins may be cylindrical, some proteins may be maybe a quadratic in nature. So usually this box is taken from the lattice chemistry. I hope you all able to recall or not. But anyway, if you're not able to recall, is no issue. We take that if we are taking any, like suppose a cubic box. So cubic box, when we are going to be taken here. So it X, Y, Z coordinates will be your X, Y, and Z. All three will be the same size. Like if I'm taking the 1 centimeter, so all three sides will be 1 centimeter. So if any globular protein is there, then that is going to be fixed there. And the tricky thing is that we can take one make question right that is we can select any box for the simulation. Yes, we can take any box for the simulation. But while simulation, it is not only the protein. We take a simulation box, then we place a protein in the center of the box, then we pour water there. So if we will take very big box, then what will be happen? So suppose that our protein has a 300 amino acid residue and is globular in nature. Okay, so hardly it will be all from X from 3D orientation, you will be get the 10 angstrom around or 20 angstrom you can take that. Suppose that we can take the 30 also. Depend on the size of the protein, global protein. So whatever the remaining area in the box, so you have to fill with the water molecules. And I mentioned that when we are applying force or when we are applying any contact, so we have to integrate for each and every atom. So what we are going to be do, suppose that we have a 300 amino acid residue, 300 amino acid residue atom contains the suppose that 20,000 and we have taken the water molecule as a 30,000. So how many atoms would be there for the water molecule? Just multiply by 3 because H2O. So each water molecule contains 3 atoms. So there will be the 1 lakhs approximately 90,000 atoms of the water molecule and 30,000 atoms will be the protein. Total system will be. And we know that this biomolecules proteins contain the charge. And when we apply the force field, charge is going to be deflect the force field. So we will not able to get the appropriate results what we are expecting. So to neutralize that, we use the counterbalance that is the Na plus and Cl minus. So when we put the Na plus, what with the negative charge on the protein that is going to be neutralized. If the protein has a positive charge, then we'll be add the chlorine minus. And if you are not able to just go to calculate that how many, one question may go, how many charge on the protein, if you're not going to bother about that, then simply add the 0.15 molar buffer of NaCl. That is going to be adjusted by automatically. And usually we use this in the just a hold. Sir, I'm in a top. Yes, sir. Yes, sir. सर एक मिनट आप होल्ड कीजिए टॉप में। हाँ सर, बात हो गई है उसकी, वो अभी तक आया नहीं है। ठीक ठीक, मैं टॉप के बाद बात करूँ। ओके, सॉरी फॉर दिस डिस्टर्बेंस। एनीवे, I forget to just mute also. Anyway, what I was talking, yes. So charge, we are talking about the charge. So then another question is where we are going to be add the charge. So we are not going to be add the charge on the protein. Okay, because so whatever the nature of the protein, we are not going to be disturbed. We are going to be, since we have put the protein there, so whatever the surrounding water molecule is there we are going to. One more thing is that we have to take care that have to make some distance between the edge of the box and the protein. So because when you will apply the force field, protein will come into the action, protein will come into the movement, and once it will come in the movement, so it will be moved like this. Okay, and when we will move, so it should be not like go just beyond the outside of the box. And this is actually this is a virtual box. This box is also used as a. I hope we all are using some Excel, some what we can say. In a school time, just we have one sheet there where we just do the plotting.
Graph paper.
That's it.
Graph
What
paper.
yeah, good. Thank you. So that graph paper. So what we are graph paper there we are getting this all a small this your a small your square. They have the some fixed width and length. So this fixed width and length, similarly, when we are taking any simulation box, virtually simulation box, we are just taking it virtually that by mathematically they are taking that okay, this is act as a grid and whatever the movement is going there. So in a you can assume that okay, they have a cubic box and in that whatever with the dimension, like if I'm taking 1 centimeter by 1 centimeter, so we have to just convert into the nanometer. Actually, these molecules are in the angstrom of size, so we are taking the usually box size also in angstrom like the 80 angstrom, 90 angstrom, 100 angstrom. This depends upon the size of the protein. But since protein is in a, they have the size angstrom, so definitely we are taking in the angstrom. So this is the very, we can assume that okay, how this the small size would be. But we have to just to understand it, we have to understand it the very large view. Just we are taking a 1 centimeter cube. So just cut the how many small cubes you can take from the 1 centimeter cubes. And that is packed there in the 1 centimeter. So each point is act as a grid. So a small and a small box like the graph paper, you will get a small square is there. They have the equal and fixed length and width. Similarly, it is there. So that is the virtually working. And virtually, we are just on that basis because some molecule is moving there and in a box. So how we are going to be calculate their movement, displacement, their velocity, and all these things. So definitely, if we have to calculate the displacement, we have to calculate the first we have to calculate the velocity. So we have to first calculate the displacement. Displacement means some from point A to B, how it's having moved. What is the time duration? What was the velocity when it's moved from here to here? What is take time on that basis? We are differentiating it. We are getting their velocity and their acceleration and all these things. So that is generating generating the just motion in the molecules, and that motion is going to be captured. It depends upon the what type of analysis you are going to do in the simulation. We are going to be captured it's in the or more very nano scale, that is the picosecond. Okay. Evenly the bond vibration is the femtosecond, 10 to the minus 15. We are going to be just record their displacement, their velocity, their potential energy, their kinetic energy. All this integration is going at the 10 to the minus 12 picosecond. So this type of a small interaction is going to be there, and this periodic boundary condition is defined that if these molecules have to be in a particular design the virtual simulation box. And this all things, if you able to have little bit, I will suggest you okay, when we are doing the MD simulation, just go some and learn some basic concepts of the chemistry. Really, physical chemistry is very essential to understand that. Okay, apart from that basic thing, now we are going to be just transforming these things in the, so we are assuming that okay, we have taken a box and then we have put it the protein and ligand there, we have put it the water molecule and the counter is there. Then next step is that the energy minimization. Energy minimization means like that. Just suppose that you have just you have rust from somewhere, go to meet someone, he meet you, handshake you, tell, okay, be sit here. Then you offer you water molecules. So just you will feel little bit relaxed. Then after 5 and 10 minutes, you will find that you are relaxed. So what we are doing here, we have taken the biological system here. We have just applied the force field. We have just added the different water molecules, counterants, all these things. So optimization process is required. Optimization, but there I have just taken the water and we have deep breath and we have relaxed. So how we are going to be optimize a molecule, how we are going to optimize a biomolecule. Optimization means okay, since we have put it there, we have put it all these things in the box. But what we have to do, then again, we have to go and check that if they have the particular distance between the atom is going to be maintained. If there have any classes, like suppose that if 3.5 this angstrom is distance required between the carbons, that is going to be maintained or not. What is the distance between the carbon and hydrogen, that is going to be maintained or not. These things, even it is not like that somewhat, because here what we are doing this by just integrating with some mathematically. And we are doing computation. So we are go and check and each every bond, bumps, and all these things. There would be no any atom class. It is not any like that. Some atom is like going to be go and superimpose with and this go and stick with it. So they all atoms because we know that. Suppose that one example I'm giving that like we have taken a two charge molecules. Okay, and we have to understand the interaction between them. Okay, and one is positive, one is negative. So when we are going to be put together and it will cross the some particular distance is going to be one atom. Then again it is not going to be solved. If we are getting the similar charge, it is they have the sum apart from that particular distance, they will be going to be effect. But once you will be go and just more and more and more, that it is going to be repel. So this type of things will be not happening while this, so we are checking it, their bond angles, torsion, their charge, all things going to be optimized while the energy minimization steps. And usually the energy minimization steps, we take the two. One is the steepest descent and another is the conjugate. So, but lots of people are asking that up to what step we have to go there. So we have to go step there. We just put it up. We are defining a force field and their achieved derivative, we are defining it like kilocalorie per moles. Okay. So this is the usually if they have the optimum like evenly if you have the more than the 100 amino acid residue protein that you can apply there. So it is going to be just optimize and adjusting all the bond and all these things. And how it is going that is suppose this value is going to like the molecule or you can say that some have you remember the molecule in a higher state, excited state. That is we're going to be just slow down, slow down, slow down in the ground state. So not directly correlated with the atom, yeah, how it's going in the excited state, and then the electron will be just maybe the external orbit, and then it's going to be down, then it will release the energy like that. But when it is going to be stabilize the molecule, so we are taking that higher energy level to low energy level. Okay. And this molecules when is travel from then one state to another state. So in between these two states, one is called the transition barrier or energy barrier. Okay. So actually, suppose that this is a well type of diagram. So this molecules is trying to be optimized there. And we are slowly going to be, but going to be down it means we are trying to achieve more and more global state. Global state means we are trying to achieve more and more stable state. Okay, because we have to do the analysis. So unless the molecule will be not in the stable state, we are not able to capture the real biological phenomenon. But when we are going, it is not like you can assume that something is packed in a box. It is not like that. It's simply just we are applying the force field and just packing all the things in a box. We have to arrange the box inside the box in the proper way, and that proper way is happening through the energy minimization. So we are going into step by step. In a step descent, initially we applied that we are not going to be taking about the whatever in the previous state. So some mathematics is here. This is the heuristic approach there. So one step is descent, it is not going to be just taken care of in the previous step. Memory, it is not going to be taken. It is a direct direction. We are forcing direction like the in the direction of the negative towards the down. And it's don't consider the history build up in the previous state. In the previous state where the molecule was, that is not going to be covered. So this is tendencies that are going to be downhill. Downhill means here, if you were to see my cursor, this is the excited state and this is the stable state. Although here it is the local energy minimum, but I am for the understanding, I am telling that if molecule is here, so we are taking it as the excited state, and the molecule is here, it is a stable state respect to this. And in this, like A, when it is going to be some is the final state here, global energy minima. So for that, they have the transition barrier. Okay, so this transition barrier is also this we can if we reduce the transition barrier, you can just correlate the transition barrier like when the chemical reaction is happening in the lab. So we know that they have the threshold energy, and unless and until for the accomplishment of any chemical reaction, that two atoms will be reached to the threshold energy, then the accomplishment of the reaction will be happen. Otherwise, whatever with the we can put the number of atoms or molecule before reaching the threshold energy, the reaction is not going to be complete. Okay, but
चलो
but
अभी आ
there
रही है
yes,
आ जाओ बच्चों तुम भी आ जाओ आज कोई भी नहीं है
okay. So to reduce it, there have some other parameter also. So if we have to just reduce it, so another factor is there we have more the temperature. So when we heat the system, the chemical reaction happens the fast. Okay. Why am I explaining it? Because after the, I will explain it after the MD simulation, we also use the entire trajectory as a reaction coordinate. And on that basis, we are also use the free energy landscape. So for that, I have explained here. But as far as the energy minimization is considered, these two steps. So first we have to go for the stepwise descendant and conjugate gradient. So like molecule is highly just occupied the large space. So we are just trying to be just make at the one place. And when it is organized, then for fine tuning, we are just applying the conjugate gradient. So in short and sweet, you can understand that when we start with the simulation, so we have added the all the atoms and all these things, mix up these things. So initially we go for the 50,000 step of the stipulation. And then once it is going to be organized, then we have to do the fine tuning. Then we apply the conjugate gradient up to the approximately 25 or 50,000 steps. So this slide will be explaining you the basic steps of the any AMD simulation, whether you are going to be to apply for the MBAR, NAMD, some Schrodinger has also whatever any method in the world you are going to be used, you have to go for this 3-4 steps. Okay, so in the right side you will get the some commands, and the left side you will get some flow chart like that. First we have to generate the topology. Topology, we have to understand that if when we are taking the any protein, so we have to convert that protein into the in a format that system is able to understand this is a protein. Okay, so that generate the topology file. So what will happen? So we know that the protein is contains of the XYZ coordinates. So we are going to be transform their coordinates. So transform their coordinates means there we are not going to be change their X, Y, and Z coordinates there. Simply format like FASTA format. Anyone have remember?
Yes, sir.
Okay. So we know that there have to be applying the simple anchor operator. So that system is going to be identified. So it is nothing there in the FASTA format. So this type of, or you can say the greater than sign, that is called the anchor operator. So that we are simply applying as a first alphabet before the given any ATGC like your nucleotide codes, DNA ATGC codes. So before that you're applying. So system is going to be, okay, from here I have to read the sequence. So similarly, we are generate this topology file there. So first step is topology file. And then I explain that you just we define a box, and after the defining a box, we are going to solvate it. Solvate means it depends upon the condition. To what condition? If there is no any specific condition, then we simply add the water molecule. If there have any specific condition, then with the water molecules we can add the other molecules also. So this preferences depends upon what type of research you are going to be do, what type of your experiment. So here when we have to do the by GROMAX, so we use the GMX PDP to GMX. PDB to GMX means start we have taken the protein as a PDB, and that we are going to be convert that in the format of the GROMAX. So simple command PDB to GMX. Then we have to define a box. So here conf is a command in the GROMAX where we will define a box, and then earlier it was GenBox, now it is the solvate. These are the command there. So this will be just solvate your simulation box. And then after the just adding the water molecule, I told you that we have to add a counter ion. So G9 will be used to add a counter ion, whatever the counter ion is required to add to the system. And this will be here add ions. After that, we have to do the energy minimization. Just we have explained you these two steps, STPS descendant and conjugate gradient. These two methods are going to be just minimize the system. After the minimization system, we apply the two ensemble process because I told you that we just whatever things is happening is the thermodynamics state that we are going to be mimic here to understand the biological system, how it is going to be behave. So for that, there have the NVT and NPT. I hope you have remembered in the chemical reaction, there have the number of molecules, then the volume, and then the temperature. We are going to fix the temperature. Similarly, there are the number of molecule, people pressure, and the temperature. At this state, we are going to be equilibrate. And when we have equilibrated that, in technical term, we call it as an ensemble state. Okay. So after this two ensemble state, after the NPT ensemble state, we have taken the coordinates and obtained coordinates will be used for the production and in the GROMACS, whatever changes just to have to do that they have the one common command that is the GROM-PP. And after that, MD run will be command will be directly go for the production run. So after the equilibration phase, we will go for the production run. This after that, no change we have to do. We have just prepared the system. We have set it. Then we have set it for any particular time like 100 nanosecond or 500 nanosecond, right? Whatever your system is going to be allow or whatever your interest or whatever your requirement of the experiment, but usually we do go for the 100 nanosecond. And just we set the all these parameters, and after that, taking the NPT ensemble, we set the MD simulation run, and that's the last command to run the MD simulation. So once you set, then after that you can do no any change in the system. Whatever the changes you have to do up to the only ensemble step, like the equilibration step, you can do any change, like temperature you want to change, pressure you want to change, anything you want to be changed, any co-solvent you want to be changed, that is up to the equilibration state only. And if you will add, like if any state we will be add anything, like after the minimization, we want to add some co-solvent and some other molecule, like some metal ions we are interested. Then again, we have to go on the from the second step, third step. So we have to iteratively, we have to follow it. Okay. So once the production line is set, like for the 100 or 500 in a second, so we have to wait for that. And once it complete, then you will be get some file as output. And your in GROMACS, you will get the .xtc file, .trr file, these two files, and the last you will get the md.pdv file also, then energy files, velocity files, all these files, outcome files you will get, and out of that files, you have to do the analysis, and that is called as the trajectory analysis. So last stage is the trajectory analysis. So we have just divided all the MD simulation into three steps. One step is the preparation phase, how we are going to prepare the system. And next, second step is the production, where we just set the MD simulation and it will be run whatever the parameter you have decided fix in the system, and it will be go up to the whatever the time frame you have set up to that it will be go, and after that the program will be exit. And then once you will get the trajectory, then we have to do the analysis. So again, this analysis, we usually do the some general analysis like global parameter analysis, like the during the simulation, what was the volume of the protein, how the protein was behaving, their structure was remain intact or not, like will be defined by the radius of the gyration, how their atomic fluctuation, that is going to be defined by the uh, RMSF, and solvent accessible area. There have the lots of a list of the analysis. So whatever the analysis you want to be do, you can do in GROMACS by using the two files. You can extract whatever the maximum of the analysis, like your XTC file and the TPR file, .xtc file and .tpr file, just applying it, and you're able to retrieve the lots of information there. As far as the application, see, more than that I have explained, but anyway, this also this MD simulation also uses a structure prediction, refinement of a structure. Evenly, one thing I would to mention that when we are getting the X-ray structure, after that we also simulate it. We apply the MD simulation because in X-ray structure, what we are getting a snapshot, a picture, and the picture of it is not like that whatever we are getting in 3D. It is electron density. So how electron density of tryptophan, electron density of alanine, and that we are going to be connecting. Okay, there have the tryptophan, there will be alanine, then there have the valine like that. Then we are connecting it on the by applying the software. So once you are because if you have seen like in the Lenja, it is also given there. You will get the some different dots there. So by collecting that dots from there, you have to resolve the structure of the protein. So software is going to be connect that dots, and that dots is nothing but the electron density of the amino acid residue. And we know the chemistry. If tryptophan is going to be attached with the alanine, so what will be the peptide bond between them, their torsion, their rotation, all these things are well studied. So on that basis, the software is going to be trained, and then it's going to be refine the structure, drug design development. Through the we are working today, we are talking drug repurposing means whatever the available FDA approved drug is there. So rather than we are doing the actually it is really the virtual screening. So virtual screening that we are taking the millions of compounds there. We can screen it against a particular target. So here more focus is that we are taking a FDA approved drug. Benefit is that once we know that if any drugs come in the market, it's have the long tenure of the various experiment and validation, verification, approval, all these things. So that thing is already approved by some agency, known agency FDA. So we are checking here that if some molecules have application in the tuberculosis, can it be explored in a cancer? So depends upon they have some protein because several times also some proteins are involved in many diseases. So in that also it will be going to be help. Or repeat this the agitated one drug is also just discovered like this. They are while doing the docking, they found it like the others there. So that's it shows the better interaction with the proteins involved in the your health, and that is this way to be discovered and come in the market. Novel molecule target identification. If there have the we can also define the molecules there. Molecular interaction is more important, and the another application is the protein folding and unfolding. So here today we will take the this one example of there have the sugar transport protein there. So agonist is there the D-glucose and antagonist is the fluconazole. So if time will permit, so we will go for the both, but one we will see how this, what are the parameter, whatever I have explained here, we will go step by step. So before that, we know that I explained that since before to start the estimation, we need a complex. Complex means protein ligand complex. We cannot assume that when we have to do the simulation. So while that we are going to be any molecular we are putting at some particular distance and it is going to be going attached at the active site. So we have to make a complex, and for to make a complex means protein ligand complex, we have to go through the docking, molecular docking. And also important that we have to just note down that whatever be the interaction we are getting in the molecular docking, that may remain persistent or may not be persistent during the simulation. Because we are assuming that MD simulation is more mimicking to the biological system. So I mentioned already that while in the initial slides that while the docking, protein are static, another ambient environment is not there. These are the some parameters, features that is locking in the docking. So that's why we found that some compounds are showing the better activity. Evenly, it's maybe happening. Some compounds are getting the very nice activity in the during the docking, but after the simulation, we'll find that his activity is not higher as we have find the docking. And some compounds in the docking are found that it is the very less active, but after simulation, we'll find that some compounds are showing the better activity. So if you are getting results because you all are some PhD students or some faculty. So while doing the experiment, you are getting such type of results. So don't be imagining that you have done some mistake, rectify the mistake with some other things. Just you have to go and you can rectify your steps are correct or not. But if you are getting this result, it means not that it is you are getting some wrong result. It usually happen. Some compounds are showing the good activity in the docking analysis that may or may not be pretend there, assume there, persist their activity while doing the simulation. Similar things happen in the experimental also. This is the reason in between the docking and the experiment or wet lab experiment, we go through the MD simulation. This is the importance of the MD simulation. After the MD simulation, we will get the some couple of plots. So the basic concept of this plots is that like first one is the RMSD. So just you can see here that it is the time is given on the x-axis and RMSD given on the y-axis. Okay. So how to interpret this plot? So to interpret this plot, during the simulation, whatever with the time frame, you all able to see my cursor?
Yes, sir.
Yes, sir.
So first fundamental principle is that as a basic man, as a layman, just to have to understand is that this coordinates is given here, x and y coordinates. 2D, this plot is there. So on the x we have put it the time and the y we have put it the armature. Root mean square deviation. Root mean square deviation tell you that is just take the suppose that when we are making a reel, so we are taking a different photographs, and when you're connecting it became a reel. So here each time, each nanosecond corresponding to a frame. Frame means suppose that my this palm is like this. So this is the first nanosecond, second nanosecond, third nanosecond, fourth nanosecond, like this. So whatever the movement is going to be taken, we have taken as the femtosecond. This you can set there. So here for to understand, I am taking as a 1 nanosecond means representing the one frame. So in that the entire protein conformation was like this. So that is going to be explained by your RMSG, RG, and SASA. So that's why it is also called as the global structure parameter. So it will define you global structure of the protein means global structure, entire structure of the protein, whether it has been distorted or not, or ligand has put any deviation in there. Deviation means disformation. We simply understand that if there have any large deviation, means there have the disformation in the actual biologically active conformation of the protein. Okay. Now to understand it, up to what extent we can go to the simulation, that also information we will get here. So here we can say that if I am taking this this green one, so you can see that green one, this initially was here, then it's take a drift. When it's go, they have any jump, then we technically we call it drift. So it's take a drift around your 5 nanoseconds, and you can see that go up, down, go up, down, go up, down, and then it became the almost stable, but the almost static. So it's parallel to x-axis. Green one, just focus on the green one. So you can see this became parallel to x-axis, and you will get the very less deviation. If I am going to be take around the your just the 75 nanosecond, if I'm going to be take. So from there to up to 250 nanosecond, you can see that there have very less changes in the trajectory. So it means that it infer that during the approximately 50 to 75%. So initially protein was conformation here. It go and jump under the force here. It's take little bit time to optimize himself, and then here to here it became stable. Similarly, if we are going to be focused on the red one, so we can see that it initially shows the very less deviation and it's achieve equilibrium very quickly. So achieve equilibrium very quickly means it's quickly become almost parallel to the x-axis. But in the green one, it's approximately after the 75 nanosecond, it's became parallel to the almost parallel to the x-axis. Similarly, we are going to be see the black one. So black one, you can see that initially it's in the parallel to the parallel to the x-axis, and after around 75 we can see there have the little bit changes in the conformation, and around 100 you can see that it is showing the, although this is going to be happen in the very 2 to 3 angstrom, okay, but this change is happening, and after that it is showing again, it's became to the parallel to the x-axis. So what this interpret that initially up to the 100 second protein was in one conformation, that is also stable. After you can say that 125 to 250 is getting the some another conformation. What is the reason behind it? That I will explain later. But right now I am simply explaining that what this trajectory is telling me. Okay. So if I am going to be conclude something from the RMSD, so here we can conclude here that there has the no major change in the conformation of the protein. Number one. Another, then again we have to do the compare between three. So what we are finding here, this red one is more stable. This black one, from this black one trajectory, we will be able to interpret that during the simulation, it shows the two major conformation. Green one shows the one conformation. Red one also shows the one conformation. But difference is that here black one is showing you the two conformation. One conformation up to 100 nanosecond and one conformation after the nanosecond. Okay, just few things we remember. I will explain what is the reason behind it. Because you say that this green one is the fluconazole, FLC, that is the fluconazole. Your SGT, this red one with the docked with the glucose, D-glucose, what I have seen in the previous slide. And third one is the simple protein. It is not docked with any line. Okay. Another interpretation that here we can say that if there have any conformation transition, protein is not docked with any ligand, it is showing the, although there have the very less difference in the different conformation state, but there have the existence of the two major conformation states. So it is also interpreted binding of ligand stabilize the protein, because we can see here that this green one also became exactly parallel to the X, and the red one is the most of the time. Okay. But on one interpretation, we cannot conclude that which compound is more active. Evenly, if you have chance that you may forget, then write down this RMSD, RG, and SASA is not telling about you the protein ligand interaction. For protein ligand interaction, we have to do the another analysis, but it is giving you the information of the global conformation of the protein during the simulation, whether the global conformation of the protein remains maintained as it is, and we assume that, because it is assumed that, and we really need it, because we are going to be do the study of the protein ligand interaction, and during the simulation, if the conformation of the protein is going to be changed, although in the biology the science of exception, so in some cases some protein go and modulate, like one of the example of the GPCR, some ligand go and bind at the intracellular domain, and it is going to be modulated to the transmembrane domain, and then they have the another active site is opening, and then the ligand is going to be bind. Okay, so this story is not there, but simple this interpretation. And eventually that we are going, so we will, that will be not going to be reflected in your RMSD, RGS. Another analysis we will be used to just explain that, okay, these things have been happening during the simulation, and that is or majorly our MPB essay is going to be decided. Another in the RG, we can see the similar pattern. After some agitation, some go up and down, the green again became stable. We can say that approximately we'll find that the red one is more stable in respect to the, and we take this water protein in the water, we take as a reference. Like if you are doing anyone have to learn the experimental. So our reference means whatever the one things we are going to baseline going to be fixed, and on that basis, because here have the three system. Two is the dog with the two different ligand, and one is the protein. So nature of the protein, And after the docking, what is going to be change happening in the protein after the docking or association with ligand? That we have interpretation. We can go ahead. If we are going to be take the SASA, so it is no major significant differences because this peak is going to be very small and up and down we are taking here because we have taken a very small scale. But once you will take the larger scale, so it will appear like a straight line. Yes. Another thing is that if we have to think about the protein ligand interaction, then we have to take in care that things come from the root mean square fluctuation. Root mean square fluctuation, this is your RMSA plot. So in a RMSA plot, you can see here all this x-axis. Now earlier what we are using when RG, RMSD and SASA we are taking the x-axis as a time. With respect to time, what was the changes happening in the conformation of the protein? In the RMSA, what we are going to be take? In the RMSA, we are going to be take that in the corresponding to the time frame, what changes you are going to be see in the particular residue. Now we assume that when we are doing the protein ligand interaction, so if any amino acid residue is not bound with anything, so it is freely to move. Okay. Once ligand will go and anchor here, so its movement is going to be restricted. But if ligand is not bind here, so its movement is not going to be restricted. So here we compare with respect to black one, whether the peak of the amino acid residue is going to be high or low with respect to the protein, because protein, it is unbound complex, there is no ligand is there, so the moment of the amino acid residue, and then after binding the what change is happening in the amino acid residue, that we able to get the interpretation from the RMSF. And this another is the ligand RMSD. So it is going, this is the active site. Here we have put the ligand there. So a spatial fitting of the ligand at the active site is defined by the ligand RMSD. Okay. So in the case of glucose, we can see here, red one is the fluconazole. So we can see that this ligand is almost remain stable, especially stable in the one particular conformation state at the active site of the protein. But at the 150, black one is the glucose one in the this this ligand RMSD. So you can say up to 150, they have the one conformation state, and then after that, it is change the conformation state. We change the conformation state, ligand change the conformation. So it was in this particular active site, and it do the something. Okay. So that conformation transition of the ligand. So you can simply compare here. If we are going to be compare this result in the with respect to the RMSG. So green one is the fluconazole and red one is the glucose. So if you're going to compare that, so here if we are going to compare the protein, so this plot is telling that the red one glucose complex with glucose is more stable than the fluconazole. But same reverse thing, you can see here that if fluconazole is especially remaining in the similar conformation transition happening in the glucose. So just contradictory result you can see. So that's why I told you this RMSG, RG and SASA give you some global information. It is particularly restricted to the protein. RG defines the integrity, compactness of the protein. If you have little bit by physical idea, there have some radius of gyration. So that we define from the center and the top, and that we are just drawing a radius. So on that, defining the shape of the protein. So the shape of the protein is during the simulation maintained or not. That will be defined by the radius of gyration. So that called the compactness of the protein. So if we are going to be put the some ligand, definitely we are pretending that we are assuming that it is not much more going to be do the change in the conformation at the conformational level. SASA, solvent accessible surface area. So simply one ligand is going to be, it is not largely going to be changed the solvent accessible surface area, because solvent surface accessible area of the protein is going to be changed. Like protein is global area, and in the water environment, if its surface area is going to be increased. So it is represent that there have some disformation in the conformation of the protein. So these two contradictory result we see here. So on that basis, here we are, it is assuming that it is looking like that. It is glucose and the AGT13 protein interaction is the more stable, but we are going to be change this with respect to this ligand agonistic. You can see that gluconazole is more stably binding the active site with respect to the your glucose. And same way we'll do the MMPV assay, and MMPV assay also suggests that this binding of the fluconazole is more stable at the active site. And the more benefit of the MPS is that it will give you a residue by contribution. And which type of contribution? It is in the terms of energetic contribution. How much delta G one particular residue is contributing in stabilizing the. I have its one table here. So you will be get after the doing MPBSA. I hope it's going to be visible to all of you. So this type of this 5 parameters here I have shown the 4 parameters, but there are actually 5 parameters there. So van der Waals interaction, electrostatic interaction, your whatever the surface and the bond interaction, all these things we are going to be. So solvent interaction also, solvent surface, all interaction we going to be considered, and then combining this we are lastly getting to the this delta G that I am going to be changing with the color here. So this delta G, so here you can see there that the glucose has the minus 23 kilocalorie per mole, their delta G value, and the fluconazole is so approximately 10 to 11 kilocalorie per mole higher binding affinity you can see in the case of the fluconazole. So up to here, anyone any question?
Sir, the decomposition plot is inverted. So as the molecule is degraded or whether its conformation was changed, that's why the graph is inverted.
What is inverted? I don't able to understand your question. Please repeat.
Sir, in the previous slide, the graph is inverted.
This one. No, actually this
Yes,
is
sir.
not inverted. Actually, I explained that this is simply telling you this is the energy, kilocalorie per mole is the y-axis, and this is the contribution of the amino acid residue. So now I hope you are able to see clearly. So it is not inverted. It is telling you that this GLN 303 and the 382 is contributing more to stabilizing the residue. So it is in the inverted, it looks like that because it is in the minus. Okay.
Okay, sir.
So here I have taken the 0 because delta G we are calculating some more and more minus means more and more affinity.
Okay. Okay.
So this is not inverted. Here I have shown you the table. So this is the graphical representation. Okay, how this molecules is which amino acid residue is going to be interact and what is their contribution. Just one second. Yeah. So here, this is the plot of the binding site active site residue. So they have the binding site. So all residue is not going to be interact or going to be, you can say that support to just maintain the interaction. But which amino acid residue involved in the interaction stabilizing the ligand at the active site, that we have plotted here, and that you will get from there also. After the MPBSA, we got this plot. Okay.
Thank you, sir.
And in this, we have simply just tell you in the terms of the delta G. So this is the total integration of that things, like how many arginine has contributed, how many tryptophan has contributed, because tryptophan would be contributing means they have the hydrophobic. Okay. Serine, there have some oxygen there, then it is involved in the polar interaction. So electrostatic, that it is going to be contributed. Surface of the protein, their architecture, the solvent, what is going to be contributed, that contribution in large set we are showing in the terms of delta G, and that plot was the individually. So, okay. Anything else?
Sir, does a solvation of the box, does it affect pH of the enzyme activity?
Actually, if we need to just fix the pH, then definitely we have to define the pH. Definitely it's going to be change these things. So what pH we are going to be done, that there have provision you can fix that pH. So that pH will be created. And if nothing pH there, then we by default we take the 7 pH. So that is a neutral by default. But if it's that's I tell you that is depends upon the nature of your experiment, what experiment you are going to be changing. Accordingly, you can change the solvent. Okay.
Okay, sir.
So I hope you all are aware with Pymol. Anyway, really not, then you can use the any visualization tool. Any visualization tool means before to just evenly do the your protein ligand docking or the simulation is always mindful that is simply you have to just open the molecule and check and mark that what are the where the ligand is there. If there is something anything associated with the ligand, so that information you will get. And eventually we have to mark the active site residue, because while the analysis what we are going to do, we have to make an index file. So whatever you have shown here that you are telling as the inverted plot, so that is the active site residue. So for that you have to create an index, and that index you have to supply there. So only in the plot that residue you only able to see. And our interest is that only active site we want to be tested to see the interaction of the active site residue, because we cannot show in the plot all the residue of the protein. Otherwise, all the residue will come. So your result will be look like very vague. Okay. So this is the protein. You can use the chimera or anything. But thing is that is simply we have to select the protein since we are before to going to we do the simulation, and then we have to save it as a mol2 format, because after that, and if you want to do hands-on with me, then you can do also. So I will suggest you when you are going to be do either another thing in the Swiss param. So see, for the protein, the parameter file standard amino acid residue, already protein, already information is there in the software. So when we will use the first command pdb to gmx, it will be converted into gromax format. Okay. But ligand is always new. So that is not you will get with the software. So for ligand, you have to generate the topology file. So what will we do here? See, this SGT glucose is here. So we need to start the simulation. We need the I put it here blue.itp, that is a parameter file. And PDB like protein, you have not to do something anything. Same thing what we are doing in the docking. In the docking, we are just clean the protein. So clean the protein means there will be no any heteroatom in the protein when we start it. Whatever we required, we will be add in the simulation. But initially there have no any heteroatom. So we have to clean the protein. And then we have to just add this. But before that, software requirement is that we need your mol2 file. So you have to submit the mol2 file. Just let me open it. So we are just doing some preparation. So we will take care from mol2 file and we will submit it. Meanwhile, what we will do? Meanwhile, we will go to our file. Okay. CD test. My screen is visible to all of you?
Yes, sir.
Okay, fine. So by using the VI edit, we just open it and we will check it. So here we can see that our protein is clear. Like in how it is going to be clear. In last line, you have to see it is a threonine amino acid residue, and the last you can see the ter and the end. So this is the end format of the any PDF file. If there would be any heteroatom, then after ter, like just I'm entering a ter, that is insert. Okay. So after ter, you will get the whatever the coordinates is given, that will be the heteroatom. So usually in the heteroatom and the heteroatom, I'm telling you whatever be anything other than amino acid added in the PDF file. So that will be comes after ter. So you have not to go and check in the entire coordinates of the amino acid residue. Simply you go in the last, you find the ter, and after that you have to simply delete it and go up to the end. So ter means file terminator. So once you will learn the protein, and then it will be read the ligand and it will be visualized there. Okay. So you can see it is the clear file. And meanwhile, we will check here. So it will take little bit time. So I hope it has been completed. So glue GP we are getting here that we have to download. I have already downloaded, but I am showing you. So I have created the new folder new, and here you will get the lots of files there, like the glue CRD, glue PAR, PDB, PSF. We need only the ITP file. So this will look like this. Okay. So what we have to do for Bromax, this simply we have to delete. So this right now I'm not deleting, but I am showing you. I have already prepared file so that I am showing you. So this is the blue parameter here. I hope I have just, yeah. So you can see it is started from the molecule type. And here you can see that this is called as the header file here. So this we have to remove it. Okay. And simply we have to save it. Similarly, we can get here. So VI, and we have to do ITP file here. So you can see it is the started from the molecule type file. Now just we have to just wait for a minute. I have to just set the GPU. Since I'm using remote machine, so I have to set the GPU in the path. Check it when we put the GMX. Earlier, when we are putting the GMX, it is not showing, but if you put GMX, so lots of command will be showing. So my first command is pdb2 GMX minus F. Sorry, but we have to go there. PDB. Yes. So in this directory, I was there, that I have. Right. So I was here, the test file is here. So now first command we have to use as the GMX pdb2 GMX minus F. Then we have to take the protein, that is the SGT 13 minus IGNH. Till we get the force field here. So since I have used here the charm, so that's why I'm taking the whatever with the here you will get the number, whatever the force field was going to be selected, that number you have to simply put. So I am putting here 8. Then you will get the water molecule, water molecule you have to select. Then we will get the 5. So see here it is showing the -3 charges here. Then we have to go to edit conf minus F. Is the conf is there. So output file would be the, we can show you the last file will be the conf file here. So GMX edit conf minus F conf. See, I have the put the ITP file just below the protein file. So it is going to be merged with the ligand and protein. So minus O, it will be easy for me to just convert it into the PDB. Then VI load dot ITP. So we have this file here, but I will not put the ITP file. ITP file will be taken by the program to recognize whether ITP file is here or not. Okay. So ITP file is a parameter file. So there we have to do the ls. So blue.pdb file would be here. So yes. So we have to just take the blue dot pdb file, and then we have to just simply copy from here to here. And gedit edit conf dot pdb. We have to open here. In the last, I told you, just here we will not put below the term. Here just we are making a one file, so we have to put here. Then we have to close this file. Then gmx. Again, I am going to be use the edit conf command because I have to edit conf minus f. Because the edit conf command, if you have remember, I have to use it for what? Minus c, just we have to place in the center, minus d 0.1, because we are taking the nanometer, so minus 0.1 is 10 angstrom distance we are going to be taking. Minus b minus o box dot pdb, and minus bt means box type. We are going to be take the cubic. Okay. Then we have to go and we have to edit in the topology file. Topol.top. So you can see here in the topology file, you will find the one information about the protein. So we have to add here. Where we will add? We will add here. So we will simply copy this line. Insert. We will paste same thing here. And we need to be file since in the present directory. So we will put only GLU. And then we will put here how many ligand is here. So we put the GLU. So now the system will be recognized. Then SPC216 minus O so underscore pro dot pdb minus p topol dot top. Okay. So here we can see that this system contained the 29,648 water molecules. Then gmx gram pp minus f em dot pp minus c sol dot pro pdb minus p topol dot top minus o em dot ppr. Then we have to add the ions. So gmx gnn minus s em dot ppr minus o ions. Since they are adding, so I have put it the name here ions dot pdb minus p name na minus एन एम पी मतलब पॉजिटिव चार्ज, एन मतलब नेगेटिव चार्ज, उसका नाम क्या होगा? नेगेटिव चार्ज क्लोरीन माइनस कॉन्क 0.15 minus tutor minus p topol dot top. Now what we have to select? We have to select 15 because we have to add the ion in the solvent environment. So it will be replace the water molecule and it will be then Bromax, Grom PP minus, then we have to go for the inorganization step. Minus C Hans dot PTB minus P to power dot tau minus O EM2 dot PPR. Then GMX ground GMX MD run minus B minus S EM2 dot PPR minus C EM2 dot PTB. It will be now just start the minimization optimization of the states. I think I have not shared the steps. The steps I have somewhere, but I will share to all of you.
Sir, how can we reduce the number of steps?
Steps, yes, we can see that also. See, number of steps to reduce that. Actually, we have fixed here force max this. Okay, 10 minus 5 they have. If you're not able to achieve it, and if you're getting some error here while the minimization, then you have to change it in the file. And this file is vi em dot. So just I forget to mention that when we run the GROMAX, we need some MDP file, molecular parameter file. You need it. So let's start MDP. So this at least six MDP file will be whatever, because I have very frequently I'm running, but like em.mdp. So your molecular simulation parameter file is there. That file you will be able to get from the site also. So once you will open the site, like here I have already opened here protein, your GROMAX site. So here when you will visit it, then you will get the all MDP file that you have to download it. But what you can do the changes there, that let me know. So here vi so see here we can change the step also, or and total whatever the we are just putting the force here, the stop minimization force, that force we can change it. This second line. Okay. Similarly, in the another file, the steps you can increase and decrease by for minimization, especially I am taking. Or in symbol state, I am not telling you right now. In symbol state, I will file open and then I will be ready. Information, what here you can change the steps. Here it is the 10,000 steps. I can put the 50,000 steps also. And this cheap derivative they are here. This if the highly diverse or highly unstable molecule, then you have to just don't put, because you can say that resolution like the in difference between the two atoms. So that we have to initially take the large. So we can put like the, it will not put like the 0.01, we will put the 0.1, then 0.01, 0.02, 0.3, like this precision we will be go. I hope it's clear to you.
No, sir.
I'm telling that in this file, like a step is given here. Okay. So but I have put in here 10,000 steps. And this dt value is given here 0.001. So if suppose that key, like you have predicted the protein or the structure somewhere else, then what you have, or your protein is not going to be optimized. So you have to put here 0.1, not rather than 0.01. So means large variation you have to take, and then slowly you have to precise. And once you're going to be precise, means up to what resolution we want to be some microangstrom resolution. उनके conformation change आना चाहिए या nano range और एंगस्ट्रॉम. So that we are going to be reduce. So जब large हमारा variation होगा तो we have to go for the large step. If there have the small variation, because we have taken the optimized, we have taken the already solved coordinates, so we have taken the very less different. There would be less variation between the two atoms. So for that we have taken the various mu. So this way we are tune it. So steps and as well as your dt, we just to have to change it. Okay. So this in the GROMAX you can set in the em.mdp and the minim.mdp. Minim means I have put a name. I will send you mdp file. I will be share with you after this. Then we have to go for the ensemble study, the npt and nbt. So gmx grom pp minus f minus c em2 dot pt. Right now again it's clear or not? Your this the steps and the force field.
Clear, sir.
So npt dot pp. And then again we have to run the same command minus b minus s npt dot minus c npt dot pt. So it will be take time. So before that, there I have somewhere. But this command I will be seeing. So this command is here. So this file I am going to be sharing. Okay. This only things is that just simply you have to use IA with a PDB to GMS. You have to add the GMS. So I will be sent to Puran sir. Okay. And you will get to from there.
Sir, do we need to install any other tools or just work on the terminal?
Definitely you need to install the GROMAX, otherwise you're not able to do it. For simulation, you need the some little bit advanced system. So I have just sent this mail to Puran sir. So collect from there. Actually, I have to rush from here, so I am just showing you final results here. So I am stopping here. It will take time. So we have already results here. So you will get results. And for to visualize the results, we usually use the XM Grace. So we'll get the different results here. One I am simply one I am showing you here. Yeah. So I told you just we did only two. These three files dot grow dot tpi and xtc file combination that we can get all the results. So gmx rms minus f center dot xtc minus s dot tpr minus o rmst dot xbg minus 2 units time unit we need it in the nanosecond. So here we have to take the backbone. So we will take the backbone. With this, I am going to be conclude here. And in the next class, I will be continuing from here. Puran sir. So whatever be the question you have.